So hi everyone, can you hear me?
Yes, I can hear you.
Okay, nice. So hi everyone. Yeah, good morning everyone. Welcome to the CVPR workshop on 3D scene understanding for vision graphics and robotics. And I'm Chu Hangzhou, former PhD student at UIUC and now scientist at Amazon. So I would like to thank you all for participating at the workshop today. And as you might know, this is our second workshop since last CVPR 2019. And before we start, just a really short recap. So let me, as usual, please let me express our gratitude to our senior organizers, Professor David Forsyth from UIUC, Professor Derek Cohen from UIUC, Professor Leonidas Gripas from Stanford, and Professor Songchen Zhu from UCLA. And thanks to our sponsor, Apple, and thanks to our co-organizers, Suyuan. Suyuan is also here. Would you like to raise your hand and say hi to everyone? Hi. Yeah. Yeah, Suyuan from UIUC.
Nice to meet you guys.
And Professor Hao Su from UCSC. Also, thanks our co-organizer, Professor Hao Su from UCSC, Professor Alexandra Shuing from UIUC, Professor Shuan Song from Columbia, and Jiajing Wu, who will join Stanford next month. Also, thanks to Suyuan Qi and Yixin Zhu from UCLA. So, okay, I think David is here now. So let's welcome Professor David Forsyth from UIUC to give us the opening remark. And you should know David because of his famous book, Computer Vision, A Modern Approach, and his outdated diving photos shown on his website. Yeah, so hi, David.
Hello, Chuhang. Well, yeah, so I thought it was best for all. Firstly, can people hear me? Let me check.
Yes.
Yeah, I can hear you.
Very clear.
I thought it was best for all that I summarize my remarks in a movie, and I believe that movie is now on the website. I sent it to Siyuan Huang.
Yes, it's on the website right now.
And I'm here mostly to say, look, it looks like an amazing program. Thank everybody for being able to participate and be creative in tremendous times, and tremendously difficult and worrying times. And then suggest we might have questions or people might prod me for further remarks on the movie.
Yeah, you can go ahead right now. Yeah, remember you will have around 2-minute Q&A after your opening remark. Yeah.
Oh, sorry, maybe I misunderstood. Do you want me to reiterate the movie?
Oh yeah, I can also share with you if based on your preferences.
Why don't we fire up the movie so that people can see it? Because I think it's more. I had a chance to edit my remarks, so the errors that I make that so amuse people are now have now been cut out.
Yeah, Chuan can help. Yeah.
Yeah. Okay. Let me see. Let me share the screen now. So can you guys see the screen now?
Yes.
Okay. Yeah.
And welcome to the workshop on 3D vision. This is David Forsyth. In a stunning display of inverse nepotism, I'm opening the workshop. I want to thank everybody who contributed. It's very hard to be creative in these extremely difficult times. And I want to note how rich the program seems to me to be. Nonetheless, I'm going to give you a list of subjunctives, and you'll see there's a reason for the biblical quote later. So let's start by thinking about the traditional picture of what vision does. So we think about recognition as solving a bunch of what are essentially classification or regression.
המיקרופון שלי עובד, אני לא יודע מה קרה פתאום פה.
Sorry, if you have questions, please raise your questions in the chat.
Yeah, so.
Yes, I will mute you right now. Sorry, you can put your question into the chat channel. Thanks.
Question problems. We identify who this is or allocate pictures of objects to categories and so on, or reconstruction. where we recover various forms of useful geometric information from images or multiple images. So SLAM, point clouds, meshes, that sort of thing. The first thing is there's lots of evidence that these threads interact, and there's lots of evidence that these activities have created value. But I also want to suggest that there is lots of evidence that these activities are shaped by what we know how to do rather than what we should be doing. What are we really good at? We're very, very good at classification. It's a recent development, but we're just amazingly good. You can classify pictures. Because you can classify pictures, you can label voxels, you can do detection, and you need to have a lot of labeled data, but that seems to be a problem that people can solve. Similarly, we're quite good at regression, probably not as good as classification, but we're really quite good at regressing things against images, again in the presence of huge quantities of labeled data. And finally, we are very good at some kinds of geometric reasoning. The basic facts of how cameras relate to one another, what you know when you see multiple pictures of an object or multiple instances in different cameras, we really know how to figure that stuff out and how to benefit from it. What are we bad at? We are bad at the unsupervised or almost unsupervised learning of visual representations, and I believe that to be a problem. We are also bad at controlling the bias of representations for advantage. We can produce high variance representations, we can produce high bias representations, but we have a tough time producing families of representations with little bias variance knobs on them. And I think we probably need to be better at that. Now, the natural question that can be asked under almost any circumstances is, will reinforcement learning save us? And I can give you a two-letter word to that answer. Here's an important difficulty. I think our actions are driven by our tools. And I'd like to go beyond the reach of our tools. Here's part of the our actions are driven by our tools case for recognition. The thing about categories is they clearly don't actually exist. Objects don't spring into being with some canonical name bolted onto their base. Any instance can belong to many different categories. So I regularly show slides of a collection of different images, ask the audience, are these monkeys? The audience is silenced because they know I'm up to something, or they may not know what it is. And it turns out that some of them are monkeys, some of them are in fact apes, and at least one of them is a little plastic toy. And also they're monkeys. Now we need to be careful when we think about categories of an argument that says, well, it's clear what makes a category. Members of a category share properties or are like one another. The difficulty we have is what properties do they share and in what sense are they alike? So if they don't exist, the fact that they're useful is kind of baffling, but they are. They're obviously very useful. They must be the product of unsupervised learning because there's nowhere else that they can come from. It really is extremely helpful to group instances together in clusters that improve prediction. So if you've been bitten by dog A, it's quite helpful to recognize that dog B is likely to bite you as well. And it will improve communication. It's much easier to complain about bitey dogs than to complain that dog A is bitey and so is dog B. Reconstructions really don't exist in any canonical sense either. There really isn't any single 3D representation because there can't be. The 3D world exists, it's not got meshes or voxels or some other such thing bolted to its base. There is no evidence that any visual task actually requires a 3D representation, and I believe it's very likely there could not be such evidence. A question you might ask yourself is, how can you determine from outside the box, without knowing what the program does, whether an agent has a 3D representation or not? It's much harder than it looks. Most things that you could do in 3D, you could also do with an awful lot of images. It's just maybe inconvenient or baffling or whatever. So we should think of 3D representations as intermediaries. And because they're intermediaries, they are useful only to the extent that they mediate something useful. So, for example, point clouds and meshes are not themselves intrinsically important or interesting. They're important or interesting because they make it really helpful for us to build, or really easy for us to build renderable models, to recover metric information, to make maps, to figure out where we are, that sort of thing. So the question to ask is not, am I correctly recovering this representation? That doesn't matter. What we should be asking is, what task does the representation facilitate, and what info does the task need? That may help us think a little bit about problems to focus on. The first thing I want to drive home, or really accede to immediately, is improved geometric models, improving the recovery of geometric models from images is always a good thing. However, I like, and I want to draw to your attention, a series of other problems. One are orphan problems, and one orphan problem I like is the space we can't see. The other orphan problem is, how do I know there is a 3D world in the first place? Other classes of problem are functional problems. Where am I? How do I get home? What could I do? And what might happen? And I'll show you a slide each on these problems with a little bit of biology for entertainment. So let's think about the space we can't see. If I want to move around, very often I might want to go behind a table, behind a chair, between two things, whatever. I'm going into space I cannot see, and I may not be able to see it until I'm really quite committed to a course of action. What I would really like to be able to do is to say, the world tells me that there is space there, or there is very likely to be space there, even though I can't see it. Now, one way you can think about this is in terms of speculated depth. Imagine I take the input image on the top left, and instead of trying to produce the depth map with the object on the top right, what I ask is, if you tell me which object is removed, I'll tell you what the depth map would look like if that object wasn't there. And the reason I care about that, of course, is that will give me some information about whether I can go behind the object, whether I can reach behind it, place my hand behind it, that sort of thing. This is difficult to do, but there's good evidence that we should be able to do it. Among other things, people regularly manipulate things that they can hardly see. How do I know there is a 3D world? This is a favorite orphan problem of mine, and one I like very much. And of course, then if I know that, how do I know how to act? One argument is I just act, I get a smack every time I do it wrong, and eventually I know that there's a 3D world. I find that argument at present unhelpful. So here are various answers that have appeared in the literature that I like. One is, if I believe that there is a 3D world, then the spatial distribution of textures is more reasonable. And that came from a paper about 5 years ago. Another answer, this you can torture out of writings by Gibson, from about 70 years ago now, that if I believe in a 3D world, the parametric forms of flow fields are more easily explained. Here is a question that follows. Do I need to know that there is a 3D world? To what extent? And I believe that question to be open. So here are some nice 3D application problems, each of which emphasizes function rather than underlying representation, and I think often leads us into surprising directions with respect to representation. So one problem is, where am I? This doesn't really get sufficient credit as 3D vision. The early work was about matching, but if I can look at a picture, match it, recover GPS coordinates, then I'm clearly doing something about 3 dimensions. And that was the work of Hayes and Afros 12 years ago now. You can think about this as non-parametric regression, and I want to draw attention to the fact that knowing where you are may not be the same as building a map. We do have quite good theories about how to recover 3D geometry from moving cameras, but they very often don't apply very well at very short spatial scales and in visually very simple worlds. So, for example, there is a mantis shrimp. This is an animal that moves really quite short distances and needs to know where it is and its direction home. And the way it solved this problem, or the way this problem has been solved for it by evolution, I guess, is it has rather special visual senses. Its eyes are extremely sensitive to polarization, and it uses them well. So from this figure on the bottom right, you can see that the mantis shrimp can rotate its eyes in 3 degrees of freedom around the stalk of the eye, that's the red arrow, across and up and down, those are the green and yellow arrows. And in fact, I've got a little piece of footage of a mantis shrimp doing quite extraordinary things with its eyes. Why does it do this? Because it can then by moving its eye, and it moves its eyes independently, it can significantly increase the polarization contrast of an interesting object from the background, and it can improve its ability to use the polarization field around its head as a compass. That compass will tell it how to get home. So here's another answer to how to get home. Desert ants, which are popular model animals for navigation studies, can wander around little bits of the Sahara Desert foraging, looking for dead insects or anything else delicious. And then they can simply turn and go home directly. Now, they can't be doing SLAM, and the reason they can't be doing SLAM is the scale of their movements and the scale of the visual features means they're not going to get very much out of SLAM. They're doing something else. It turns out that you can explain their behavior without even needing to suggest that the ant maps. Instead, there are a series of different cues available to it. Again, the dead reckoning, the polarization, and the like, each of which produces a go-home vector. Then the ant produces a weighted combination, and when it decides to go home, it just leaps onto that weighted combination vector. And of course, it's got to do a little search when it gets close to home. Here's another important problem for thinking about with respect to 3D representations. What can I do? Now, you should notice that path planning is really not about geometric detail. Geometric detail creates fantastic complexity in path planning, and it means that generations of computational geometers have had to worry about how to get oddly shaped objects through oddly shaped gaps in free space. But mostly our experience of movement in the world is not like that. We appear not to need to solve fantastically hard computational problems to get around. If one looks at moderately modern path planning methods, they emphasize random sampling, so you have rapidly expanding random trees, that sort of thing. And they emphasize reusing things that you know will work in the past, so nearest neighbors math. And you can look at these and think of these as strategies to duck detail. You really actually don't want geometric detail because it's a nuisance. What you need is a test that says, if I do this, will I have a collision? Now, what that to me says is we should be worrying about why we are recovering details from images rather than worrying about being able to answer this query. If I do this, will there be disaster? Similarly, we should be thinking about the geometric affordances of objects. What can be done to this object and where can I do it? This likely isn't inherited from categories. So by geometric affordance, I'm referring to the property of a doorknob that makes you want to put your hand on it, the property of a mug handle that makes you want to put your hand on it. These are not necessarily categorical properties. They're geometric properties. We are remarkably good at looking at things, recovering their geometric affordances and using them. This may be why one can reach out, pick up the handle of a knife, and then stick its head into the head of a screw, thereby violating all sorts of rules of decency. So here's a fun little movie about geometric affordances. The mantis shrimp that I mentioned has excellent polarization vision. We know that strain fields inside objects have a very significant effect on the polarization of transmitted and reflected light. Watch the little mantis shrimp here. What it's going to do is wander up to a clam, look at it, move it around into position, and then whack it, and the clam will break. The question you could ask is, does its polarization vision mean that the clam shell has a sort of hit here tag in the way that doorknobs have a grasp here tag? Here's another function of 3D, which is very important. It allows us to reason about what might happen, or it explains to us what might happen. I can show you this movie because nobody was actually hurt, but the full movie is wrenching. So here we go. Really not much. Ordinary day on a platform. Still an ordinary day on a platform. Not much happening. Not much happening. At this point, it is apparent that something very bad might happen. And I believe that that's an intrinsic property of 3D. It has to do with reasoning about movement and space. So here I want to suggest some conclusions. Right now, what we do is shaped by our tools. And that is because our tools are powerful and exciting and new. Those tools encourage us to collect a data set, regress, and repeat. But 3D representations are mostly intermediaries. You don't really know what to collect a data set for unless you're collecting the data set for a function. And the intermediaries we should be looking at are ones that are task appropriate rather than generic. I find the following problems appealing, although everybody's mileage may vary. Please enjoy what seems like a very rich program of exciting research in these and other areas. Stay safe in terrible times. Thank you.
Yeah, thank you, David, for the talk. So right now, we can have a kind of a short Q&A question. I think we are only available for one Q&A question. So if you have any question, please click the raise hand button, and then we can unmute you, and then you can ask David. Tash, okay. Tushar Vaidya. Yeah.
Yeah, hi, this is Tushar. My question, yeah, first of all, thank you, Professor, for a wonderful approach described here. So, my question is like, can you explain a little more about what do you mean by we don't need a scalar precision based SLAM, and we can solve the approach even without solving, we can solve the navigation problem without solving the SLAM? Like this is more of I am seeing from the perspective of bio inspired, the way humans do navigation. What I believe is like humans navigate by calibrating its eyes. From a childhood, humans calibrate their eyes and then they capture the 3D world. It helps them navigate. So yeah,
So
over to you.
let me try. So the first thing I want to be very careful about is I'm not arguing SLAM is not useful or we don't need SLAM. There are very clear cases where SLAM is very useful, then we do need it. But there are situations where you might not be able to do it, or it might be overkill. So again, if you think about it, this desert ant, firstly, it doesn't have a tremendous amount of smarts. So it's not really in a position where it is advantageous to the ant to have a full map. It's also got a very serious problem, which is it moves on very short scales, and the scale of the geometric detail available to it is not very good. So imagine you were a desert slam and a desert ant, and you did SLAM, it might not tell you very much because there would not be very much detail available, a good reconstruction available to it in the first place. The final thing is, from the ant's perspective, it doesn't really need a map. What it needs is where to go to get home, which is not the same thing. So if it can do a little maintenance on a vector that says go this way, you'll hit the entrance to the nest in this distance, and you might have to do a little bit of search. That's probably enough. So the argument I'm making is the kind of 3D representation you may want to recover from imagery may be unlike the familiar ones. And there may be many things that recover such representation. That's not an argument against SLAM. It's just an argument that says when you can't do it or you don't want to do it, there are a whole bunch of other things you can do that may solve your problem. The other thing that one sees in the sort of bio-inspired world of navigation a lot, just how useful matching waypoints can be. Right? If you think of the world as a bunch of waypoints with associated information, you can do a great deal more than most people would think.
Great, great. Thank you for the answer, Professor.
Thank you.
Thank you, David. Sean, you're muted right now.
Yeah, thank you, David. Sorry for the time limitation. We have to move to the next speaker. Yeah, you're really inspiring talk, David. Thanks. So next, let's welcome Professor Andreas Geiger from the University of Tübingen. And Professor Andreas Geiger has the Autonomous Vision Group at U of Tübingen, located in Germany. Yeah, welcome.
Hello, thanks for having me. So I'm trying to share my screen. So I thought I'd do it live. It's a bit more personal. Can you hear me?
No. Yes.
Yeah, very clear.
Okay, good. Can you see my screen?
Yeah.
Yes. Good. Yeah, so let me just quickly shoot up a timer. Thanks for having me. Actually, it was a great talk by David, and despite I fully agree with David that the downstream task matters more than the 3D representation, I want to talk about 3D representations today. My talk is titled Learning 3D Reconstruction in Function Space. And this is joint work with a bunch of collaborators, my PhD students, Lars, Michael, and also Sebastian, who's Microsoft Research in Cambridge. So The goal of my research group is to make intelligent systems more autonomous, robust, and safe. Now, intelligent systems must interact with a complex 3D environment. I always like to show this little video. This is a ZG generated environment, but it shows like how complex that can be in terms of geometry, when you need to estimate affordances or measure certain distances in order to actually achieve a certain goal in that environment. Now, 3D reconstruction is a hard and actually quite old problem that dates back to the 50s. A traditional reconstruction pipeline takes a set of images as input and first computes camera poses using structure from motion, and then finds dense correspondences. Of course, there's different flavors to this pipeline. So one approach is to find dense correspondences, create depth maps, and then fuse these depth maps into some more coherent, larger scale 3D reconstruction, which can be refined at the mesh level if desired. However, humans are actually able to recognize 3D even from a single 2D image. If I show you this image, you can exactly tell me how far approximately that refrigerator is, and if this chair is in front of the oven or not, or what would happen if you would move forward in this scene. So a natural question to ask is, well, can we teach computers to do this, to infer 3D even from a single 2D image? And that's basically the setup that I will talk about here in this presentation, where at a very high level, the input is a single 2D pixel map. And then there's some neural network that maps this pixel map to a 3D shape. Now, it's relatively clear how the input is represented. It's this pixel map, but how should we represent the output such that it's easy for a neural network to predict that output? So what is, in other words, a good output representation? There's various representations that have been used for deep 3D reconstruction. It's not that old as a field, so it started maybe in 2015 with this IROS paper. And the natural way was to use voxels, which are a discretization of the 3D space into a regular grid. Here, a 2D and a 3D example on the right. And the advantage of voxel-based representations is that they are easy to process with neural networks, because you just need to define or generalize 2D convolutions to 3D convolutions. However, they are inherently limited in terms of their memory assumption, because the memory grows cubically now compared to image-based tasks, which limits their resolution. And they have a Manhattan world bias. So you need to determine somehow you like canonical coordinate system here. Another representation that have been used are point sets. Point sets are a discretization of a surface into a set of 3D points. However, point sets do not model connectivity or topology, and existing approaches are typically limited to a small number of 1,000 points. Furthermore, it's harder to encode local information, so most approaches use a global shape description, and we will see some of the deficiencies later on also for our model. Another representation are mesh-based representations. Mesh-based representations are also a form of discretization. In this case, a discretization into vertices and faces. Meshes are also limited in the number of, or existing deep learning-based approaches that output meshes are limited in the number of vertices and therefore the granularity that it can produce. And more importantly, they require either a class-specific template that is deformed like a human face or a human body, or they lead to self-intersections or non-watertight meshes, as in the case of AtlasNet here at the bottom right. And the reason is that meshes are just a very complicated construct to predict using a deep neural network. It's very easy to produce these self-intersections. What we have been proposing at CVPR last year is, instead of using an explicit representation, to use an implicit representation, which does not need discretization as the previous approaches, and which can model geometry at arbitrary topology and resolution, which has a relatively low memory footprint and is not restricted to a specific class like the mesh-based approaches. So the key idea is very simple. Instead of representing the 3D shape explicitly, we instead consider the surface of the object implicitly as the decision boundary of a nonlinear classifier. So here we have a neural network, F, parameterized by a set of parameters theta, that maps a 3D point location, and an image condition that's encoded into some latent code using an image encoder. Maybe this is a 128-dimensional code here, to an occupancy probability. So for instance, here in this example on the right, all the red points should be classified by this classifieds, effectively mapping the reconstruction to a classification problem, should be classified as inside, and the blue points should be classified as outside, or here for this bench. The red points are inside the bench, the blue points are outside the bench. So it's a supervised machine learning problem now. Also want to mention there's a couple of concurrent work. There's, for instance, a work that used, instead of an occupancy output, a assigned distance field as output, and this works equally well. Now, such a model can be, because it's a classification network, can be trained using a standard classification loss like binary cross entropy. What we do in practice is we sample a mini batch of 2,000, around 2,000 points, and then minimize the sum over the binary cross entropy between the ground truth label. So we assume there's a label data set of points that we can draw from, and these points have inside-outside labels, binary labels. So we want to minimize the distance of those with respect to the predictions of the model for the corresponding point P that corresponds to O. And C here is the condition. This is the image encoding. We can also create a generative model easily from this approach, which we call a variational occupancy encoder. It's basically a VAE formulation of our model, which has the BCE, the cross entropy, as a reconstruction loss, and additionally this KL term here that basically compares the encoded distribution to the standard normal distribution. So we have an additional encoder cube psi here that takes a set of points and occupancy labels and maps them back to the latent code, as in the regular VAE. So let's look at some results. It's easiest to show these in the video. I hope that plays well. So what I can see here is single image reconstruction results. So all methods get a single 2D image as input, and they are tasked to reconstruct the shape of that image. So here's a voxel-based baseline. This is the result of a point set generating network. This is the result of a mesh generation model. And this is our result. Of course, because our model doesn't explicitly represent the surface, we need to use an additional procedure to actually derive the mesh from the representation. And we derived one, the details are in the paper, that basically hierarchically looks through the volume and hierarchically queries the volume depending on if a point is inside or outside, and looks at places with finer detail more frequently than at places with less detail. So that's the way how we construct these meshes out of this model then. Here are some results for point cloud completion. So we can use a different encoder for our model. In this case, we encode a point cloud using a point net. It's a coarse point cloud. And then on the right-hand side are the reconstructions for the different baselines and for our approach. As you can see, even from such a coarse and noisy point cloud, we can recover quite smooth and complete surfaces of the ground truth. Here are some voxel super resolution results. In this case, the task is to take as input a coarse voxelization of the shape, and we want to recover the fine details. And here on the right are our results, on the left is the ground truth. And the same results for a bench. We can also use our model as a generative model, and what we show here are latent space interpolations. So these are novel shapes generated from our model by traversing the latent space. And these novel shapes are, of course, not part of the training set. So not all of them look realistic, but you can see that it interpolates reasonably well. Okay, so the next thing we ask is, well, can we also learn something about object appearance? Everything I've shown so far was only about geometry. And we can actually use a very similar idea, mapping implicitly a point location now not to an occupancy value, but to a color value. So what this texture field model that we've presented at ICCV last year does is it takes a 3D geometry that could be either a cut model, or it could be a geometry predicted using, let's say, the occupancy network, and a real image, and tries to produce a textured version of that model by assigning to each 3D point a color value. So here are some details about the model. It has basically an encoder for the image as the previous model. It has a encoder for the shape as, and then we produce a depth map for the target shape in order to query the 3D points. This is just to reproject into 3D space and to get actually the 3D point locations that we want to query the texture field. And then we pass both the 3D point location, the image encoding, and the shape encoding into a neural network that predicts for that particular point the color value. And we train this model using a reconstruction loss. We can also produce a variant of our model. There's a generative version. So for instance, with an adversarial loss function here in a GAN style. So in this case, the latent code is drawn from a random distribution. We don't have a reconstruction loss, and we have a discriminator of unpaired images. We can also produce a VAE version of the model where we have, again, the reconstruction loss, but now the image is encoded using the VAE encoder into a latent code and then decoded again where the reconstruction loss is compared. We can look at how good this model is first by comparing its representation power to a voxel-based approach. So what we did here is we overfit to, in this case, the cat. So on the left, you see the ground truth. In the middle, you see our overfitting results. You can see that we can recover relatively fine details, but at some point, our details are limited. So it's not recovering all the details of the ground truth. However, what we show in the paper is that our representation in terms of bits to store is much more compact as if you would store a voxel-based representation. The same here for a human body shape. So let's look at some results of that model. So these are, again, single image reconstruction results. Here on the left, you can see the input image. On the right, the ground truth shape. In this case, it's actually the ground truth shape that corresponds to this image, but it doesn't need to be. We see some results later on. And here are some baseline results. This is a novel view synthesis baseline that only operates in 2D space. It's very hard for the novel view synthesis baseline to produce consistent results, as you can see, from just a single image as input. Normally, these novel view synthesis methods get hundreds of images input. In contrast, the texture field approach is consistent by definition because it produces a 3D output. And also, it produces much finer details in terms of appearance. Here's another example. And here's the texture field result. We can also get texture reconstruction from real images that were not part of the training set. So here we have paired a real image with a cut model, and this is the texture that is applied to that model when we do inference. And now we look at a full pipeline where both the geometry has been predicted using an occupancy network, and then on top of that, we predict the texture. Of course, this is a very simple example. There's actually a lack of databases for photorealistic examples at high quality. So we use ShapeNet here. And here's some latent space interpolation. You can see the same latent appearance code applied to different CAD models. Okay, so, well, now we've seen these implicit representations might be useful for representing geometry and texture, but what about motion? Motion in 3D. It turns out that extending the occupancy networks to 4D, from 3D to 4D, is actually quite hard. And the reason is the course of dimensionality. Representing a 4D space is just much harder and requires much more capacity and much larger data sets, which particularly in 4D are not available. What we do instead, or what we propose to do instead, is to represent the shape only at a particular point in time using a 3D occupancy network, and represent the motion by a temporally and spatially continuous vector field. Now, this is a 4D field, but the advantage of this is that this is a very smooth vector field compared to representing the shape over all time instances. And the relationship between a 3D trajectory and the velocity is, of course, given by a simple differential equation, which is the location differentiated with respect to time is simply the velocity. Now, we use recent advances in differentiable ODEs in order to backpropagate through this differential equation here. The approach is illustrated schematically here. So what we do is, so at t equals 0, we represent the shape. What we do now is if we have an observation at t equal tau, so this is the time tau, then we warp this observation. So we have the ground truth label here. Let's say this is inside the human body. So we warp this label based on the ODE through this vector field back to time step 0. And then we can evaluate our model, our occupancy network at that time step. And then both the occupancy network and the velocity network are conditioned on the input x in order to derive such representations from image or video or point cloud sequences. Right? So this is the way we train the model. So the nice thing about our model is that no correspondences are needed. They are implicitly established by our model. You can see some results here where you can see color-coded the same parts of the human body. We didn't require these correspondences at training time. They were automatically established during training. Here are some results. These are for point cloud completion. You can see very coarse and noisy point cloud as input on the left. And you can see what happens with a naive 4D extension of the occupancy network idea, which leads to impoverished results, in particular in the arm areas. This is the result of a point set generating network in 4D, and this is the occupancy flow approach. Okay, here's another example. Input point cloud and the occupancy flow approach. Okay, so this is all nice. But one advantage of the classic explicit representations is that there exist differentiable rendering algorithms that allow for learning these representations from images alone. All of the results that I've shown you so far require complete 3D supervision. That's why we applied them to synthetic images. So the question is, well, for these implicit representations, can we also learn these implicit representations using 2D supervision alone without requiring 3D geometric supervision? And it turns out yes, and it turns out that even a simpler architecture can be used that combines appearance and geometry in this case. So what we have again is an image encoder that produces a global image, a global appearance code for that image. And then we have this point here in 3D space. We have actually multiple of these points. That's why it's a vector or it's a matrix of n points times 3, which is the x, y, z coordinates. And we feed both of this into this implicit network, which is 5 ResNet blocks conditioned. Every ResNet block is conditioned on the input encoding. And then we have just 2 shallow heads, one for the occupancy and one decoding the texture information. And we do this in parallel for around 2000 points, just because memory is sufficient to do this for many points in parallel. So that's why we have these matrices and this vector here as an output. So the nice thing is here, now we have just one model. We don't have a stacked model of first predicting geometry and then texture, but we predict both simultaneously. Now, in order to learn this from images alone, we need to define a differentiable renderer. And in terms of network terminology, this requires us to implement a forward pass in PyTorch and a backward pass in PyTorch. The forward pass is the rendering pass. So how does this work? Well, here's an illustration with an image plane and a camera center and a ray that corresponds to pixel U that marches through 3D space here. And you can see this thick gray line is demarking the level set, the decision boundary of the classifier with parameters theta for the current condition. So this is where the surface lies. These thin gray lines are either in front or behind the surface. Now, because of course we cannot directly find the surface point, what we do is for all pixels U, we find the surface P hat along the ray via ray marching and then root finding. So we march along equidistant values along the ray, distances along the ray, and query the occupancy network. And then once we found a change in sign, then we can apply a standard root marching routine in order to find a zero crossing efficiently. So we use the second method here. So this is the surface point that has been retrieved. Then we can evaluate the texture field head. So this is the texture head from the model that I've shown at that particular location, which gives us a color. And then we can insert that color at that particular pixel. And if we do this for all the surface points, we get an image. Okay, so that's fine. But how can we implement a differentiable backward pass for this? So for the backward pass, what we want to do is we want to compare the prediction to the observation. So here you can already see the observation is slightly different for illustration purpose than the prediction. That means we want to make the prediction look more like the observation, right? So we want to change basically the occupancy network and the texture field in order to match the observation better. So how can we derive gradients for this in this implicit model? Well, we first compute the loss between the prediction and the observation as common. And then we compute the gradient of this loss function with respect to the parameters of the network I've shown before. And that's just a simple chain rule, and it requires the derivative of the predicted image with respect to the parameters theta. So far, not surprising. Now, this predicted derivative with respect to parameters theta is the total derivative expression that we see here on the right-hand side, because both the texture field as well as the prediction P hat through the occupancy network depends on the parameters theta. That's why we get this sum. So these terms are all fine, but they are readily available using standard backprop. But how to compute the derivative of the 3D point with respect to the parameters theta that appears in this expression? It turns out that differentiation of the surface constraint, this is the surface constraint, implicit differentiation of the surface constraints yields an analytic solution to this problem. And here on the bottom, you can see the solution to this problem. So this is nice. Now I found an analytic solution which allows us to change the both the texture field and the occupancy network such that the observation aligns, or the prediction aligns more closely with the observation. The nice thing about this analytic solution is also that it doesn't require storing intermediate results. If you have a voxel-based differentiable renderer, you need to store intermediate results along all voxels along the ray, which is quite memory intensive and limits to small resolution. Now we don't need to do this. We can directly just update at the surface point. So here are some qualitative results for this. On the left, we first see the input image, and on the right, the results of soft rasterizer, which is a mesh-based approach that predicts from a single image using only 2D supervision at training a 3D model. Here are results from pixel to mesh, which actually requires 3D supervision. And here are the results of our approach using only 2D supervision. Of course, this is pretty hard for this untextured object. If you add depth maps, which are easy to add in this formulation, you get slightly improved results. So it can handle both depth maps and RGB images. Here's another example for a car. Pixel to mesh using 3D supervision. Our approach using only 2D supervision and using depth maps in addition. Here just showing the geometry. Here's an example for a plane. We have also applied our model to real multiply reconstruction on the DTU dataset. So this is a real dataset, and what we did is, because the number of images is limited, so we cannot do single image reconstruction, we overfit our model, this implicit model, on a particular set of images from this dataset. And this is the results. While the images from the dataset do not cover the full object, our model is able to produce a watertight mesh. still you can see some errors, but at least you get a water type mesh out of it. Okay, so that's all. Let me conclude. In summary, I've presented neural implicit models as an effective output representation for shape, appearance, material, motion, and so on. They do not require any discretization as explicit methods do and model arbitrary topology. They can be efficiently learned using 2D supervision, have many applications in reconstruction, view synthesis, segmentation, and so on. But there are some challenges. Geometry must be extracted in post-processing step that takes about 1 to 3 seconds for ONet. The extension to 4D is not straightforward due to the course of dimensionality. And this fully connected architecture and the global condition that we currently use leads to oversmooth results. However, there's some promising directions. For instance, you can use local features as in our convolutional occupancy network approach or in PyFu, or a better input encoding as in NERF. That's all from my side. I want to thank you for your attention, and I want to point you to this link here, which is our research blog if you're interested in our work.
Yeah, thank you, Andreas. Yeah, so I think due to the time limitation, you might have. So I think right now there's already a lot of questions posted in the chat room. So you can pick one to reply them in live. And then if you have time after that, you can directly just feel free to use the chat room to reply to all the questions. Yeah.
Sure. Yeah. Okay. I need to pick one. Good.
Or too short, one long or too short.
Yeah. Okay. I picked the last one. How is the training and inference speed using implicit function? How well can I generalize? Oh, this is a lot of questions. Okay. So training time, it's true that actually these models train very long. So if you train them for a week, results still improve. So typically we train for a few days, but even after 2 weeks, the results improve. And we found that using either the idea of local features or better input encodings can significantly improve training time. And then the other one was how well can it generalize to unseen classes and real captured images trained only with ShapeNet synthetic images. We had some results on the video for the TextureNet, for example. So there is some generalization, but all of the, I mean, it's all very preliminary. So all of our images are relatively small resolution, right? And so ideally we have a real data set, and we hope that like with differentiable rendering techniques like DVR, we can get to the point where we can actually train on real data sets without having to know the ground truth. I will answer the others in the chat.
Yeah. Thank you very much. Yeah. Thank you, Professor Andreas Geiger. So next is, yeah, thank you. Now let's welcome Professor Jeannette Bohg from Stanford University. And Professor Jeannette Bohg enjoys research at the intersection of robotics, machine learning, and computer vision applied to problems in robotic grasping and manipulation. Yeah, come. And you can directly share your screen to show.
Thank you very much. Let me do that, share the screen. Just a second.
So there is a green button like in the lowest part of the Zoom.
All right. Okay. I hope you're seeing my slides. Yes. I'm just going to assume you do.
We're not seeing it right now. Maybe
you're not seeing it.
So Sean, did you give permission to her? Let me check it.
Because I see that I do share on my side.
No, let's check it again.
I can stop it again and reshare if that helps.
Yeah, try that. Zoom has this issue that it doesn't share the first time.
Okay, let me try again.
I think it works now. Yeah.
We see something was black.
How about now?
It says you're sharing, but you're black. Maybe try again.
Every day, something new with Zoom.
Yeah.
Okay, how about now?
It's not working.
Okay.
So did you stop it and reshare it?
Yes, I did.
Oh, it works.
All right. Give me one
Good
second.
enough, Jeannette. Proceed.
Yeah, just that I wanted to actually play with this. Okay, so I assume you see presenter mode.
Yes.
Okay, thanks. How about now? Do you see the full slide?
Yeah.
Yeah.
Very clear.
Perfect. All right. Cool. So welcome to this Zoom talk, and I'm sorry for the technical difficulties. I guess every one of you who tried to present to Zoom went through some of these iterations. So thank you to the organizers for inviting me. I'm very happy to present today. It's kind of sad that all these conferences are remote, but you know, I usually don't come to CVPR, so it's nice to be able to reach out to this community. Okay, so today I wanted to talk about why depth data is actually very important for decision-making and robot manipulation. And just to give you an idea, here's a video of one of my favorite robots, actually at the MPI in Tübingen, where Andreas also used to be or still is. And this is Apollo, and it's supposed to grasp the Springles box while not knocking anything of the other stuff on the table over. And Jim Mainprice here is just basically bothering the robot and like putting things in the way. And the robot really has to react in real time and change its plan. And so there are lots of things going on here under the hood. I don't even want to talk about all of them. If you are interested in them, check out this paper. But one of the things that I want to emphasize for this talk here is that the ability of this robot to perceive the environment in 3 dimensions is crucial for it to make this decision about how to move its arm, where to grasp the object, and so on. And just to give you an idea of how this roughly looks like, here you see what the robot sees. So in the background in gray, you have like this typical depth map coming from a Kinect, right? And then overlaid in this rainbow color scheme, you have an occupancy grid map where basically the height is encoded by color temperature. So the warmer the temperature, the higher the object. Yeah, so if the robot is basically acting in the scene, it has to react to whatever, wherever the object is, whatever kind of obstacles are in the way, and continuously adapt, right? So for any kind of these manipulation tasks in dynamic environments, 3D information is crucial. And so I hope I convinced you with this, or gave you an idea of why I think that. And it's kind of surprising that many of the recent very successful robotic grasping work, for example, the Google Armform here, the 2 versions of it, are actually relying on RGB data and maybe some four-stroke data as well, but mostly RGB data. And it's very surprising to me because I would say that using more modalities should actually including depth, should actually be useful, and you should actually need less data in order to train your robot to grasp anything. So that's really our hypothesis, that the more modalities you have per data point or per kind of trial the robot is doing, the more accurate you should be in your either perception task or really manipulation task. So for reaching the same level of accuracy, you may need less data points if you include many more modalities. And why do we think that is? Because multiple modalities basically provide rich data, more information, and the data is also complementary. So just as an example, this is from a work we have published like last year at ICRA, where the robot basically has to do a manipulation task. In this case, it's a peg insertion task, and it gets basically RGB and depth data as well as force-torque data. And Michelle here, she's like tapping on this force-torque sensor at the end effector of the robot to basically disturb the robot and see if it can recover. So this is just an example manipulation task. And what I want to emphasize here is that, or I want to show you a bit like that actually each modality really contributes to the success of this task. Here are some results from this paper. If you want to look more at these, at this particular paper, where the contribution is really learning a multimodal representation for the robot, check it out here. We basically did some ablation analysis in simulation, where we randomized this location of the box with the hole, and we showed that if we use all the modalities, so RGB information, depth, and touch information for the robot, we achieve a success rate of 78% in this tag insertion task. And now if we remove one of these modalities, we see that the success rate actually decreases. If we remove RGB, we get some drop. Typically the robot is not able to actually fully insert the peg. If we don't add touch, it's really struggling with peg alignment, so it's actually like moving the end effector to the right place. But the biggest drop, to actually our surprise, comes from not including any depth in the image. And it struggles really with the alignment of the peg and the hole. So depth is really important for these kind of spatial manipulation tasks. And another important benefit of depth data for manipulation is that it transfers way better from sim to real than RGB data. So, and here are just like two example projects where we have shown this. I think other people have also shown that these are the ones where we trained the robot in simulation entirely, or in the right project, we actually, it wasn't a manipulation task, it was a perception task for instance segmentation. So in both of these cases, we trained the model that we used, or the policy that we applied in simulation using depth data, and it transferred to the real world without any fine tuning. So I think this is also an important point on why using depth data in manipulation tasks. So maybe to summarize this point, really, a robot has not just RGB cameras typically, but in particular, this robot has also, of course, depth sensors, even stereo sensors, and maybe in the future we should, in robotics at least, include all of these sensors that such a robot has, not just vision. But today I want to talk about two projects where we really needed to rely on depth data to solve a more difficult task. So the first project I want to talk about is a project where we wondered if we can actually pick up any kind of object.
It's an initial 3D bounding box and calculates the corresponding.
Excuse me?
With 3D GCK, we propose an extension to object detectors to enable 3D object detection from monocular.
Someone is having a talk at the same time I'm giving a talk.
As a basis,
maybe the host could mute Jun 1.
Yeah.
Thank you.
With 3D GCK, we propose an extension to object detectors to enable 3D object.
Sorry about that. Yeah,
no
continue.
Problem. Okay. The perks of having a virtual conference. Okay. Sorry, where was I? Okay, so in this project, the problem that we wanted to solve is to pick up any object with any kind of hand. So imagine you have a model trained on a robot with a particular hand. Maybe, I'm guessing you're seeing my mouse here. maybe with this leftmost hand, and then you want to apply the same model on a robot that has this particular hand, or even a 5-fingered anthropomorphic hand like this one. And in this project, I want to show you how we use depth data to actually be able to transfer even between these different hands. It's really important to recognize that in grasping, the geometry and kinematics of these hands interacts really with the geometry of the object. Okay. So a good grasp really depends on both the object and the gripper geometry. And we proposed this unigrasp model for grasping any object with any gripper. And specifically, the approach that we use is that unigrasp outputs contact points. So as many contact points as there are fingers in the specific hand. So here are some examples. And how does our this unigrasp model look like? So basically, this model takes as input an object point cloud and a geometric and kinematic description of the robot hand. So it's in the URDF, it's called a URDF file, but it's basically a geometric and kinematic description of the robot hand. And then sequentially outputs contact points that are both reachable by the gripper and in force closure, meaning it's a stable grasp. What we found in the end is that we can grasp novel objects with various grippers and actually achieve then a 90% grasp success rate on these. Okay, so let me get more in detail into this model. So basically, unigrasp extracts gripper geometry and kinematic features from this hand and concatenates them with object features in the encoding stage. And let me first explain this gripper feature. So basically what we do is we parse this URDF file, which contains the kinematics and the geometry of each of these hands. And we basically render a point cloud of these and then do a simple autoencoder to basically optimize reconstruction loss. So this is our representation model. And then for the actual full gripper feature, we take each hand, move it to the joint limits that it has, compute for each of these configurations a feature with this encoder, and then concatenate it for the full gripper feature. So with this feature, we then encode basically both geometry and kinematics. So this was about the gripper feature, how we do that. We also compute basically object feature, where we just use an existing model. We basically use PointNet++ to encode this point cloud from an object and then concatenate it with into one feature, the gripper feature and the object feature. And really the algorithmic contribution of this paper is in this part into the staged network that outputs sets of contact points for the finger. So basically, given an n-fingered gripper, this contact point selection network will have n stages. And in the first stage, the model first predicts the probability of each of the points of the object point cloud to belong to a stable contact point sets. And then this model ranks the points of the objects and selects the top K1 points. And then conditioned on the first selected point in stage 2, it then predicts the probability for each object point. Again, on whether the second contact point is also still part of a stable set of contact points for the hand, and so on until, in this case, we have 3 contact points that are basically stable, result in a stable grasp, but are also not in collision with the object, right? So the hand is not somehow intersecting with the object. So this is what this contact point selection network does. So there's a lot of complexity in this network. I'm not going to talk about this in detail, but please feel free to look at the paper that I will have referenced later. So I just want to show you first how the learned gripper embedding works by visualizing the interpolation in the gripper feature space. So first, we basically generate 2 point clouds of these 3 different grippers each, so one closed, one open, or one in particular configurations, and then we basically move in that configuration space in a straight line. Here what you see in the middle is basically the corresponding reconstructed point clouds. And what you see is really that when you interpolate between these configurations of the hand, you, for example, see here how the gripper is really opening. Here it's really changing one of the fingers to move over. And here again, it actually interpolates between different hands in a reasonable way. So these are just like 3 examples for this. Here's something interesting that actually hopefully brings again the point home that the geometry in grasping depends on both on the geometry of the object and of the kinematics and geometry of the hand as well. So what you see here is a black point cloud. Looks a bit funny, but this is basically a point cloud of some object. In red and in yellow here, or here in green as well, you have basically the contact points that our model outputs given this object point cloud and this specific hand. You see here, for example, for this first hand, that this one has a very small opening, so it can only grasp very thin parts. So the model actually generates contact points that are really at this thin part of the object. And this hand has the same geometry, but different joint limits. So you see that it generates contact points actually at a much thicker part of the object that are potentially more stable actually for this hand. And here again, you have a hand that has 3 fingers, so it has to generate for the same object, again, different contact points. You see, for example, the red contact point is at a different position from the first one. All right, so we also wanted to know if we can basically grasp novel objects with various grippers. This is the set of objects that we considered. Here, the set of hands that we considered. And by the way, these are all real robot experiments. And by the way, again, this model is trained on simulated data that I'm going to talk about in a bit, and then just basically used in the real world. So first, here's an example of a robotic hand grasping novel objects. So the model was actually trained with this hand. So the hand here is not new, but the objects are. Again, we also wanted to know what happens if you have a new hand, or if you change the design of your hand slightly. We also wanted to understand if we can grasp novel objects also with novel grippers. And here are some examples where we have trained with this hand geometry, except from the trained model had 3 fingers available. In these examples, the hand can actually only use 2 fingers. We also have examples with this 4-fingered hand that, again, the model has also never seen before. So it only has this geometric description of it. And yet again, it can do fairly difficult grasps with these kind of slippery fingertips as well. We have failure cases still that are typically due to imprecise perception or low friction of the object, some premature contact during reaching, or object deformation. Yeah, so just to summarize this work, so if you're interested in more detail, especially about the point set selection network, please check out this paper. And the main idea here was really to generate finger contacts given an object point cloud and a kinematic hand description. And the algorithmic contribution in this paper is the point set selection network that we propose. We achieve a 90% grasp success rate, even with novel robot hands that this model hasn't seen before. So one thing I haven't told you before is how we trained this particular point set selection network. And basically what we did was to generate data in simulation, where we basically loaded a bunch of about like more than 3,000 objects, recorded them from different viewpoints, and then we used 11 different hands to actually grasp them. I want to get your attention to this particular box. So we basically did not hand label these, but we used a well-established metric within robotics to automatically label grasp as good or not. But one maybe problematic point with this, or one point where this metric is lacking, is that it doesn't generate grasps that are good for a particular task, but rather they're good for picking up an object, no matter what you want to do with it afterwards. So this is really a standard metric, but it's not task specific. This is another problem we were interested in. How can we manipulate any kind of objects for some kind of manipulation task? So let's say you're asking this robot to pour you a cup of coffee. Then it has to kind of figure out how to grasp this object. And also it has to be able to transfer this knowledge to any kind of instance of this object category. And one of the challenges with this kind of task-specific grasping is like a total lack of data in this field, or like typical data sets are pretty small. And especially these existing data sets typically only have, if they have 3D data, they're very small. But if we are looking at, for example, these kinds of human activity data sets, they are typically in 2D only. So they're not very useful for a robot where it matters to take geometry into account, right? So we have these interesting data sets that are very rich in the kinds of manipulation tasks people are doing, but they're pretty useless for a robot as they are. So if we wanted to have a robot be able to do task-oriented grasping, we want to somehow be able to extract 3D information from this data. All right, I'm going to skip this and just go to exactly the idea that we had. So we really wanted to leverage these very rich human activity data sets to find distributions of human grasps on, for example, these different kind of object categories, to then actually transfer them to a robot. Okay, that's our goal. And what that means is that we need to have some method that lifts the hand object pose in these 2D images to 3D. And one of the things that we're gonna leverage is something that also already other people figured out, is that hand pose, if you know the hand pose in the configuration in an image, and actually also helps you to estimate the object pose and shape, and vice versa, okay? And in our approach, we essentially propose a new network that outputs, that jointly estimates hand and object pose. And then we can run this model on these huge data sets that are out there for human activity data, and automatically label different object categories of where is actually a good pose to grasp them or not. And once we have this data, we can teach a robot on how to use it to do task-oriented grasping as well. So, so this is basically a summary of this approach. I don't know, maybe the organizers can tell me how much time I have left, since I've lost a few minutes in the beginning.
You have 3 to 5 more minutes.
Okay, thank you. So essentially, if we open the box of this this approach, we have essentially 2 parts to this. We have a hand predictor that we train on the first-person hand benchmark to predict hand pose and joint configuration of the hand. And then we have an object predictor that is also, again, trained on a synthetic data set, because there is no real data set, and outputs a pose and the shape of this object. So specifically, the input that we have from this grasped data set is segmented image, including the occlusions. And we have the ground truth pose, because it's synthetic, right? And we also noticed that if we include this information about the hand, we are actually achieving a better object pose estimation. For retrieving the shape of an object, so we don't directly estimate the shape of an object, we actually retrieve it by using the image as a lookup in an embedding space where each point is basically associated with one of the training data points. So that's how we get a pretty good estimate of the object pose and shape, including the hand. So here are some example outputs. And we also compared to another method that it's not category based, but directly tries to estimate object shape. And here's some example outputs that we ran on the same data. And one of the problems is that the objects are typically very blob shaped, maybe because there is a prior on this. And we found that shown here in green, we can basically improve object pose estimation and shape estimation in terms of position orientation, in comparison to this work. All right, so we have this network that basically lifts 2D data into 3D, and now we can automatically annotate 3D objects with where are good places to grasp, and basically then train a task-oriented grasping module to give to the robot. So here's some examples of how these real 3D point clouds are being labeled. Red means not good to grasp, green means good to grasp. And we also have some stability estimator here that we merged to then grasp this with the object. So summarizing this part of the work that was done by Mia. So this is the title of the work. If you want to know more about all the details, there are actually a lot that I had to skip. So the main idea is really that we want to leverage these very rich activity data sets that show humans manipulating objects. But we need some way to get the 3D data out of it to make it useful for a robot. And the algorithmic contribution was really a novel hand-object pose estimation network. And the result is a more accurate pose and shape estimator that we can then demonstrate, or that we can then leverage in a task-oriented grasping module that we demonstrate on a real robot. So just to conclude, I showed you two works that really are examples where 3D geometry or depth data is extremely important to make the right decisions in robot manipulation. The first work was about using any kind of hand that hasn't been shown before. And it was really crucial to use 3D information to actually be able to transfer to novel hands. And in the second work, we first needed to process a 2D data set to lift it into 3D so as to make it useful for a robot. So with this, I want to close this talk. Thank you very much for attention. I'm also thank my funding sources and my collaborators from these different places. Thank you very much.
Yeah, thank you, Jeannette. So thanks, very nice talk. I think there's one question posted in the chat room. So you can, maybe you can just directly reply that. And for remaining questions, you can directly go into chat with them in the chat room. Yeah.
Sure. Should I reply right here?
Yeah.
Okay. Okay, so the question is, this largely planar environment, how does depth provide a significant benefit? And so I haven't shown what the robot actually, it looked on the side at this scene. So depth, there's a lot of foreshortening. So that means depth gives really much more clear information about what the relative alignment between the end effector and this hole actually is than, for example, RGB. And the size of the hole, it's so small, it's so few pixels that it's not going to be useful for this kind of very precise manipulation task, right? So there are just a few millimeters that are actually, for which it has clearance. All right, okay, I'm happy to answer any other questions.
Yeah, thank you. Okay, so I think, yeah, if you have more questions, you can just post it in the chat room and also just discuss with Professor Jeannette Bohg. Yeah, thank you for coming. So next, due to the time limitation, we might just directly move to our first hour presentation. So here we'll have 3 invited papers, and so I will just directly share screen and post all the pre-recorded videos. And if you have any questions to the authors, just feel free to put it in the chat room and directly chat it with them. Yeah, I think I will share screen then. So can you guys see my screen now?
Yes, you can.
Okay, good.